Okay, let's unpack this. Have you ever felt just buried under too much information?
Oh, absolutely.
Like you need a shortcut to actually understand what's important, what connects, and, why.
Definitely. In today's world, with data just flooding in, that feeling's pretty common.
Right. So finding systems that don't just store stuff, but actually help you navigate it, make sense of it quickly, that's becoming critical.
Exactly. And that's why we need better tools, better structures.
Precisely. And today we're diving into something really fascinating from a technical paper, the metamorphosis. It's a concept they call the Fractal Identity Map, or FEM.
Right.
Think of it as like a radical new architecture for organizing huge amounts of data. It's designed to make complexity feel, I don't know, manageable, clear.
Almost like the data explains itself through its structure.
Yeah. So we've dug into the source material you shared, pulled out the key ideas.
And our goal here is to walk you through it. So by the end of this, you should have a really solid grasp on what the FM actually is.
How it works under the hood.
The mechanics. And why the paper suggests it could be a real game changer for things like AI, managing complex data.
And even potentially how we might interact with computers using our brains. That sounds wild.
It's definitely out there, but the potential is fascinating. Let's get into it.
Okay, let's jump right in. What exactly is this fractal identity map at its core?
Okay, so at its core, the paper describes a FEMM as a multi-dimensional hierarchical system. It's specifically for organizing identity representations in data.
Multidimensional hierarchical.
Okay, and it's fundamentally a computer science concept, right?
Yeah.
Meant for software, processors, hardware.
Not biology. The paper mentions the brain sometimes.
Right, but that's more of an analogy. It's illustrating potential structural benefits, maybe computational advantages. It's not claiming the brain is an LIM or vice versa.
Got it. So it's an engineering approach for computers. How should we picture this structure? It sounds complicated.
Well, conceptually, you could visualize it maybe as an n-dimensional matrix or grid. Think of a cube, but maybe with, many more axes than 3.
Okay, a multi-dimensional grid.
Or maybe picture something like a multi-tree grid.
Yeah.
Where you have these tree-like hierarchies extending out in several directions at once.
A structure spreading out in multiple dimensions. And how does it actually place data within that structure?
This is where it gets really interesting, I think. Data elements get organized using what the paper calls self-legending semantic addresses.
Self-legending semantic addresses. Okay, break that down.
Basically, they're hierarchical prefix labels.
Yeah.
But the key idea, the really core concept, is that the location of an element in this structure, that is its identity and its context.
Wait, so its coordinates tell you what it is?
Exactly. Location is meaning here. The address itself encodes the semantics.
Location is meaning. Wow, okay, that's a big shift from just like arbitrary memory addresses.
It is. The structure itself encodes meaning, and that's why they also call it self-similar or fractal.
Fractal, like the patterns.
Precisely. It refers to a structural property. The way it's organized repeats at different scales. If you zoom in on any part of the map,
it looks like the whole map, just smaller.
Structurally, yes. The organizational pattern is analogous, which gives it a certain consistency.
So the rules are the same everywhere, big or small scale.
That's the idea. And crucially, it's not static. It's not a fixed thing.
It can change.
Yeah, it dynamically adapts.
Yeah.
Based on semantic weight distributions in the data. So as relationships or importance shifts, the map can actually reorganize itself to reflect that.
That makes sense. Data changes all the time. Okay, let's get into the nuts and bolts then. How does this actually work? What are the mechanics?
Okay, so it starts with that hierarchical prefix structure we mentioned. Think about each dimension, each axis of this n-dimensional grid.
Right.
Each one has its own hierarchy of prefix labels, a bit like, folders and subfolders in a file system.
So a path like maybe science, then biology, then genetics could be a prefix path along one dimension.
Exactly. That kind of idea. But these labels are semantic. Now, layered onto this is a really key mechanism. Weight-based ShortLex ordering.
Weight-based ShortLex ordering. That sounds important.
It's fundamental. This is how the FM really bakes meaning into the location. At any point in the hierarchy, the children elements, the things branching off, they're sorted, not just alphabetically, but by descending connection weight from the parent.
Connection weight, meaning like importance or how often they're linked.
Could be either, or frequency, relevance, whatever measure of significance matters for that data. The most important children come first in the list.
Okay, the heavy hitters are listed first.
Right. And then their prefix extensions, the next part of their label, are assigned to preserve that weight order lexicographically. using a rule called ShortLex.
ShortLex, what does that do?
ShortLex means basically shorter prefixes always come before longer ones.
Yeah.
And then for prefixes that have the same length, they're sorted alphabetically or numerically.
Ah, okay. So length matters first, then alphabetical.
Exactly. The paper gives an example. If you have labels A, A1, A2, AB, and B, the ShortLex order would be A, B, length 1, alphabetical, then A1, A2, AB, length 2, alphabetical.
Got it. A and B are shorter, so they come first. Okay, so the insight here. By combining the weight, the importance, with this ShortLex ordering, you're structuring it so the most significant items automatically get the earlier, more prominent addresses.
Precisely. You are embedding significance directly into the structure, into the address space.
That's clever.
And remember, this is multidimensional. So an element's full address, its actual identity, is a multidimensional coordinate. It's a tuple, a set of prefixes, one from each dimension.
Like prefix dim1, prefix dim2, prefix dim3.
Exactly. So if, say, dimension 1 is subject and dimension 2 is context, an item's address might be something like science prefix, research paper prefix.
Combining these different semantic angles?
Yes. And the intersection, where these prefixes overlap across multiple dimensions, that defines a specific block or region of the map. The paper calls it a semantic spatial submatrix.
A submatrix.
Yeah, and everything within that region is semantically coherent across those specific dimensions you looked at. So examining these submatrices lets you focus on really localized patterns within this huge semantic space.
Okay, so the structure isn't just storing data, it's actively organizing it by meaning, by weight, by relationships. And its position is its meaning. Let's talk payoffs.
Yeah.
What are the key features, the big advantages of doing things this way?
Well, one of the most significant is how it handles identity and meaning. We've said location is identity, right?
Right.
This enables something called meaning propagation downward. Children automatically inherit the semantic context of their ancestors.
How so?
Well, if a high-level prefix, way up the tree, means something like highly trusted source, then everything below it in that branch automatically inherits that trusted attribute. You don't have to label every single point individually.
That's efficient. Saves a lot of redundant tagging.
Exactly. And the flip side is precision reinforcement upward. As you add more prefixes, go deeper into the hierarchy.
You get more specific.
Yes, you refine the meaning, increase specificity. And, conversely, if you move up the hierarchy, you get generalization.
Zooming in for detail, zooming out for the bigger picture.
Precisely. And that's fantastic for systems like AI. If it can't find an exact match for a very specific query.
It can back up a level, find something more general but still relevant.
Exactly. It provides a natural fallback mechanism.
Okay, that's powerful. Now, another major claim is built-in interpretability and explainability. How does that work? This is a huge deal in AI right now.
It really is. And this might be the standout feature of the FEM, according to the paper. The coordinate, the prefix address itself, is the explanation.
Oh.
It's self-legending, as they put it. The address itself tells you the context, the lineage, how it got classified. The structure is the explanation.
The map is the model. I saw that phrase.
Yeah, it's a powerful way to think about it. The shape of the data within the map, its position, reveals its context, its significance, maybe even its causal lineage.
So you can just look at where something is and understand it.
That's the goal.
Yeah.
And it enables very fast reverse traceability or lookup. Meaning, if you have a piece of data, or maybe a signal from a brain-computer interface, and you know its prefix address, you can instantly trace it back up the hierarchy, understand its origin, its context, why it ended up classified that way.
So if you see, like, signal B2 on the emotion axis,
you'd know instantly it's the second most significant item under the top-level category B for emotions, whatever B represents.
Wow. So no digging through logs or complex debugging to figure out why an AI made a decision or where data came from. You just read the address.
That's the promise. And they claim this explainability is essentially constant time, technically OE time.
Oh, what's E?
E is basically the sum of the depths, the number of prefix levels across all the dimensions for that specific data point's address.
Yeah.
The point is, each node can store a fixed-size summary of its key context, and weights, they call it a metavector.
A summary vector.
Yeah. And fetching that summary, that metavector, is very fast, like O1 cache fill once you've found the node.
Yeah.
So the explanation for any given point is available almost instantly.
Constant time or near constant time explainability. That's incredibly valuable, especially as systems get more complex. Okay, what about overall efficiency, searching through this thing?
Right. The hierarchical structure and the prefix matching allow for significant skip logic.
Skip logic?
Yeah, you can effectively bypass massive, irrelevant sections of the data space when you're searching or processing.
How does that work?
The paper talks about an exponential search reduction. They quantify it with a factor like CT raised to the power of n.
Ah, CTN.
Yeah, think of it this way. If at each level in the hierarchy, across n dimensions, you only need to look at C-relevant categories out of a total of T possibilities.
Okay.
You're reducing the search space you have to scan by roughly that factor, CD multiplied by itself n times.
Whoa. If C is much smaller than T and N is large, that reduction is enormous.
Exactly. It can be a dramatic speed up. It embodies this idea, the source notes. Focused attention is all you need.
The structure guides the attention.
Precisely. This also leads to entropy reduction. By pruning away all those irrelevant branches, you're reducing the uncertainty in your search.
That makes sense.
The paper even uses this cool phrase, faster than wind Cartesian lift.
Faster than wind.
Yeah, it's describing how applying simple local rules operations that are fast, maybe O1, at each node across the E levels of a hierarchy, can multiply up to generate exponentially powerful semantic results, potentially identifying up to C to the power of irrelevant items, but with only linear work, like OE effort.
So the structure itself is doing the heavy lifting, amplifying simple actions.
That's the concept. The intelligent structure guides you directly to what's relevant super fast.
Okay, that's efficiency. What about managing change? Data evolves? Is it stable? Or does meaning drift around vaguely?
That's another key point. Resistance to semantic drift. It's designed to handle this through a threshold mechanism. Yeah. Unlike some other data representations, like maybe continuous vector embeddings, where meaning can shift gradually, ambiguously.
Right, the drifting embedding problem.
Exactly. Here, identity is anchored to these discrete prefix paths. Things only change position, get reclassified, when the aggregated semantic weight, the strength of connections, the significance, shifts enough to cross a predefined threshold.
Like statistical significance?
Could be, yeah, like p.05 or some other measure. It means it takes a substantial, meaningful change in the underlying data relationships to actually make something move in the map.
So it avoids that constant, fuzzy, maybe meaningless drift. Reclassification is a distinct, explainable event.
Right. You can say, this data point moved from prefix X to prefix Y because its aggregated connection weights changed enough to cross a threshold. It's not a black box mystery.
And that metavector you mentioned helps here.
Yes, that aggregated context stored at each node provides stability. The inputs or outputs related to that node have to change substantially past that threshold to trigger a reclassification event.
Provides stability and transparency.
Okay, and how does this whole structure fit with modern computing? Parallelism. Hardware.
It seems really well suited for it. The prefix-based structure naturally supports parallelization and hardware readiness.
How so?
Well, different regions of the map, defined by different prefixes or combinations of prefixes, can be processed pretty much independently.
Ah, so you can assign different branches or submatrices to different processor cores or compute nodes.
Exactly, with minimal interference. And that relatively low OE computational cost per node that we talk about, that supports linear weak scaling, meaning as you add more processors, the system can handle proportionally larger problems.
Built for scaling.
Seems like it. And the structure is also described as being amenable to mapping directly onto specialized hardware.
Like FPGAs or ASICs.
Potentially, yes. Custom chips that could perform this kind of semantic routing and data access extremely fast, maybe with better memory locality too.
Interesting. And they again mentioned the neuromorphic analogy here, the structural similarity to brain topography, suggesting potential designs for brain-inspired hardware.
Yeah.
But again, analogy, not direct copy.
Got it. So it seems designed with parallel computation in mind from the start. Okay, let's tie this all together. Where do the potential applications really lie? You mentioned AI and BCI earlier.
Right. For AI, the FEM offers several things. Semantic partitioning, helping to untangle different factors in complex data because they live in different parts of the map.
Makes sense.
The skip logic enables focused inference. The AI doesn't waste time on irrelevant data sections. It zooms in on the right prefix regions.
Efficiency again?
Yep. You could potentially train parallel submodels on different prefix-defined regions of the data, and it offers a path towards interpretable semantic memory. The FEM itself could act as a structured, understandable long-term memory for an AI.
And the explainability is baked in.
Crucially, yes. It's not an afterthought you try to bolt on later. It's fundamental to how the data is organized.
Explainable AI. That's such a huge need right now. This sounds like a really direct approach.
It does. Then for BCI, brain-computer interfaces.
Hmm.
This is where it gets really interesting, I think.
Yeah.
The M could potentially map neural signals or sensory inputs directly to prefix addresses based on where they come from in the brain or their context. Treating, as the paper says, space as symbol.
Space as symbol, mapping brain regions or signal types to addresses.
Kind of. And the key idea here is overcoming traditional bitrate limitations in BCI.
Cow. BCI struggle with them getting enough information through, right?
Right. Instead of trying to transmit tons of raw neural data, which is high bitrate but maybe low on immediate meaning, you could use the FEM to encode complex meaning into a deeper, more specific prefix address.
So you scale the meaning conveyed by making the address longer and more specific, rather than just trying to push more raw bits per second.
Exactly. That's the fascinating idea. A short prefix might mean a very broad concept or category, but a much longer, deeper prefix could encode a highly specific thought, intention, or percept.
It creates an exponentially expanding semantic vocabulary using the prefixes.
Precisely. It leverages the combinatorial power of these hierarchical prefixes and that reverse lookup capability we discussed.
Yeah.
That would allow tracing a BCI signal, represented by its prefix, back to its likely neural origin or cognitive context, which could be huge for things like associative memory interfaces.
Wow, that's a really elegant potential solution for BCI bandwidth and meaning. Okay, how does this whole FIAM concept stack up against, other ways we organize data, databases, knowledge graphs, etc.?
The paper touches on these distinctions from prior art briefly. It acknowledges that FIAM combines features seen elsewhere hierarchy like tries or quad trees, spatial locality like quad trees or space-filling curves, semantic richness like knowledge graphs.
So it borrows ideas.
It integrates them, but the paper argues the synergy is unique and non-obvious. The key differences highlighted are it's fundamentally weight-driven, it's multidimensional with symmetrical semantic axes, it specifically maps semantic space, not just geometric. It provides that built-in interpretability via location by design, it has the thresholded resistance to continuous drift, and it's explicitly engineered for parallelization with those OE performance bounds.
So it's the specific combination and the resulting properties like built-in explainability and drift resistance that make it novel.
That seems to be the core claim.
Right.
It's presented not just as an improvement on existing tech, but as a fundamentally different architectural approach to organizing information.
Taking proven concepts but weaving them together in a new way.
Right, to unlock these specific benefits.
And we mentioned dynamic adaptation earlier. Just to recap clearly, how does it handle data changing or new stuff arriving?
Right, it's designed to be adaptive. So smaller changes in those parent-child connection weights. They trigger local reordering. The children just shuffle their positions based on the ShortLex rule to reflect the new weights.
Okay, local adjustments.
But more significant shifts in weight, the ones that cross that predefined threshold we talked about, those trigger discrete reclassification. The data item essentially gets moved. It's relabeled with a new prefix address that accurately reflects its new semantic significance and its proper place in the updated structure.
So it actively maintains its own organization as the data itself evolves.
That's the goal, yes. And it supports adaptive insertion too. When new data points arrive, they can be placed into the correct spot in the hierarchy based on their connection weights, fitting into the ShortLex order, potentially in real time or incrementally without having to rebuild the whole map from scratch.
Which sounds essential for any real-world system dealing with live changing data. Okay, and just quickly, that mathematical context, again, you mentioned E and C2. Simple takeaway.
Sure. E is just the sum of the prefix depths across all dimensions for a point.
Oh.
Main takeaway is that operations at a specific node, like fetching its explanation or checking for drift, take time proportional to E. It's a measure of the complexity of that specific location's address.
Okay, so E is about the cost of work at a location.
Right. And CTN represents that potentially massive exponential efficiency gain you get from the skip logic when searching or filtering across the map.
Gotcha.
It shows how focusing on relevant paths off to T cross dimensions lets you ignore huge parts of the space. So E bounds the local work, while CTN explains the global search efficiency.
Local work is linear in E, global search gets an exponential boost. Got it.
Exactly.
Okay. So bringing this all back together, the fractal identity map, as laid out in the metamorphosis,
Yeah.
seems like a really powerful and, yeah, fundamentally different way to think about organizing information.
It really does. By embedding identity, meaning context, directly into the location of data within this adaptive, weight-ordered, multidimensional structure, it creates systems that are sort of inherently interpretable. They're incredibly efficient because of that intelligent skipping. They're resistant to that ambiguous semantic drift.
Yeah.
And they're built for parallel computing from the ground up.
And we saw how this architecture could really shake things up in areas like AI, especially explainable AI complex data management, and maybe even break through limitations in things like brain-computer interfaces by scaling meaning itself.
Yeah, it really shifts the focus. It's about making the structure of the data do the heavy lifting and providing context, relationships, and explainability, moving beyond just storing data points to creating an active map where position and relationships are the meaning.
Okay, here's where it gets really interesting then, thinking beyond the tech. This whole FIS concept suggests that complex meaning can emerge directly from structure, from spatial relationships, much like, the brain seems to organize information topographically.
That connection is provocative.
So given that, could thinking about organizing information this way as a dynamic, weight-sorted, multidimensional, self-similar wrap, could that fundamentally change how you, listening right now, approach your own learning or your memory or how you structure your own knowledge and ideas?